sure replace it. So the fundamental theorem of algebra, you'll actually already know what it is because I've been telling you about it since we've done polynomials. It is basically how you know how many roots there are. So if I asked you how many solutions should I get, how many solutions do you think I should get based on this equation? 4. That's what the fundamental theorem of algebra tells us. But we're going to go a little bit more in depth with how many real and complex. But they ask us to find the solutions. We're going to discover that, of course, there are 4. But I do want to show you how many could be imaginary or real. So if I were asked to find the solutions, I would factor this using a quadratic pattern. So act as if this were an x squared, but instead of putting x and x, we'll put x squared and x squared to get back to x to the 4th. Numbers that multiply to 4 and add to negative 5 would be a minus 4 and a minus 1. Now, if the direction said factor completely, I would factor each one further. Since it just wants to know the solutions, I'm just going to go ahead and use the zero product property. Solve, add 4 to both sides and square root. I'll get plus or minus 2. The other one, add 1 and square root. Plus or minus 1. Identify each solution as real or imaginary. So our plus or minus 2, real or imaginary? Real. How about this one? How many solutions are there? 4. Okay, now just to save us time, I'm not going to have us solve the next one. I'm going to tell you what we would get since we're on a 2-hour delay schedule. If you were to factor and solve this, you would end up getting x equals plus or minus I square roots of 3 and plus or minus 2i. That's what you would get if you factored this. Classify each solution as real or imaginary. Would this be real or imaginary? Imaginary. And this one's also imaginary, right? How many solutions are there? 4. Now, what you want to remember is that imaginary solutions come in sets of 2, right? Imaginary solutions like 2 plus 3i, we know its conjugate to minus 3i would also be a root. So if you have one imaginary root, you have 2. So the imaginary roots come in pairs. So you're either going to have 0 of them, 2 of them, 4 of them, 6 of them, 8 of them, 10 of them, when you're looking at how many roots you're having. Now, rational roots do not come in pairs. If I told you x equals 1/3 is a root, that does not mean x equals negative 1/3 is a root. Remember, that only works using your imaginary root theorem or your irrational root theorem, which was your irrational root. So if we had, I guess I could say that too. Your irrational roots also come in pairs. Those would be your 2 plus the square root of 7 and 2 minus the square root of 7. So these would also come in pairs. Or sets of 2. If you have one, you have the other, as long as it satisfies that the coefficients are rational, which they always will be when we're doing these. But your rational roots do not have to come in pairs. They can come in singles. Just 1/3, just 2, just 5. And then the conjecture down here about the number of zeros of a 4th degree polynomial, we obviously know that there would be 4 zeros. Now, some of those zeros are going to be imaginary, some of them are going to be real, and that's something we're going to talk about on the back. And I'm going to try to explain this better than last year because some students got confused. Okay. So the fundamental theorem of algebra just tells you that you have at least one complex root, but that's not the one that we really use. We look at the corollary a little bit more that says if you have a polynomial that is an nth degree polynomial, that's the largest exponent, then it has exactly n roots. So the largest exponent is the number of roots you will have. And again, I've kind of harped on this since chapter 5, when we did quadratics. Like if it was a squared, we had to have 2 answers. No, if we did a cubic, it was 3 answers. Now we see quartics, we should have 4 answers. Now what makes these questions here below confusing to students is that they ask you for a number of different things. Some people either don't list all the things they're asking for, or they get them confused. So I'm going to try my best to explain this as well as possible. For each of the following equations, we're asked to find the number of complex roots. Now, what confuses some students is that they think complex is imaginary, but really, complex can be real or imaginary. It's like an overarching title. Because if you were to have 3 plus 0i, that would really just be 3, right? Which is then a real number. So really, complex numbers are like an overarching. So anytime you see find the number of complex roots, I want you to think of the total number of roots. And I think that's something that confused students last year. So they thought complex meant imaginary. It doesn't, it means total. Complex, imaginary, or real. Kind of combine this together. So this one would have 4 total roots. Also known as complex roots. So that's the first part to the question. Now, they ask us for the possible number of real roots. How many real roots will we have? Not telling me what the real roots are, just how many possible are there. So you have to think that from the total roots, it's split up into real roots and imaginary roots. And the problem with this question is that it doesn't ask you how many imaginary roots that you have, and you really need to think about that in order to answer the question. So remember, your imaginaries come in sets of 2. They don't ask you this question. You have to, though, think about it in order to answer what they've asked. So imaginary roots come in sets of 2. So of the 4, you could have 0 imaginary. You could have 2 imaginary, or you could have 4 imaginary. Now, to figure out the real, these have to add together to get us back to 4. So if I have 0 imaginary roots, that means I would have 4 real roots. If I have 2 imaginary roots, 4 minus 2 would get me that I'd have 2 real roots. If I had 4 imaginary roots out of 4 total, that means I'd have 0. So this is the answer, 0, 2, 4. That's part 2 of the question. Part 3 is find the possible rational roots. Now the possible rational roots are what we did before, which are our factors of the last term over factors of the first term. So factors of 3 over factors of 1. So our possible rational roots are positive, negative 1, and positive and negative 3. And I kind of want to change the next example. Let's change the 4 to a 5. Sorry if you already did it. Just because otherwise it's too similar, and I want you to see one that has an odd root. Alright, leave everything else the same about it, doesn't really matter. So, 5th degree polynomial. Total number of complex roots would be 5. There are 5 total roots. Again, of these 5 total, they're going to break down into, some of them could be real, and some of them could be imaginary. The imaginaries have to come in sets of 2 because of the conjugate, the 2 plus I, 2 minus I concept. So the imaginary is always going to be even pairs. 0, 2, 4. I'm not going to list 6 because you can't have 6 answers if there's only 5 total. Now, when you work backwards to figure out how many real solutions there are, you have to do subtraction. So 5 minus 0 would be, I could have 5 real solutions. If I have 0 imaginary out of the 5, there's none that are imaginary, that means I have 5 real. If 2 of them are imaginary, 5 minus 2 is 3. If 4 of them are imaginary, 5 minus 4 is 1. So the number of possible real roots are 1, 3, or 5. It doesn't matter which order you put them in. Some students just like to memorize if it's an even number, the number of reals are evens. If it's odd, the number of reals are odd. But this is why it occurs, and it's because the imaginaries always come in sets of 2. Okay, last thing we're going to list then, so that's part 1, part 2, part 3. The possible rational roots would be factors of 1 over factors of 1. That's easy. Plus or minus 1. And I think last year what confused some students was saying the number of roots, which are how many you have, and then listing the possible roots. They just got like confused with like what was being asked of them. All right, last set of problems ask us to actually find all of the answers. Made these text boxes, but you didn't have them on your sheets. Find all the zeros. Find the number of complex zeros first. So remember, complex means total. So that's 3. Now this kind of goes back and reiterates what we did last week. Remember, you can list all the factors of 8 over factors of 1, test them all in your calculator, use synthetic division and the quadratic formula. But what's a much faster way to find all of the zeros for this one? X equals?
I don't know.
Augie? Good. Factor by grouping. If you can factor, you definitely want to do that. On your quiz, which will be this Friday, many of them will be factorable either by grouping or using a quadratic pattern. It will save you a significant amount of time so you finish your quiz in time if you do factor when possible. Okay, some of them will not be factorable and you'll have to do that, but take out your GCF here, which would be x squared, and your GCF here, which would be 4. And simplify that down. And then find each zero using your zero product property. Should get 2 imaginary plus or minus 2i out of that one because we subtracted 4. And then we also should get x equals 2. So see how the imaginaries always come in sets of 2 because of our plus or minus. The next one we can also factor by grouping. What would the GCF be for the first set? X to the 4. And the GCF for the second? Negative 1. Now, before you start taking fourth roots of things, okay, you do actually want to factor this one down further so that you make sure you don't forget an answer whenever you're doing your roots. So this would be x squared plus 1 and x squared minus 1. And then you would just finish by finding all of your answers. Should get plus or minus 1i, plus or minus 1, and negative 3. And that does get me a total of 5 complex roots. Mason?
Should the middle one be factor more?
It can be, yes, if you wanted to. Since the directions just said solve, you don't have to factor further. If the directions had said factor completely, then yes, we would definitely want to. But once you get to that x squared, it will, when you add 1 in square root, it will get you both answers. So your homework is 6.6 homework, which is on the website. Make sure you answer all of the questions like we did up here, where you're telling me how many total, how many real, and then listing the possibilities. Tomorrow is a practice day.